we're going to be talking about intramolecular forces and intermolecular forces. An intramolecular force is within the molecule, like an intrastate is highways that go within the state, while interstate highways go between states. An intramolecular force is our actual bonds, like covalent and ionic, while intermolecular are going to be between the molecules, and when the molecule goes from solid to liquid or liquid to gas, these are what are being broken, the intermolecular force. The types of intermolecular forces that we're going to be talking about are dipole-dipole, London dispersion, hydrogen bonding, ion-induced dipole, and dipole-induced dipole. A dipole-dipole attraction is seen in molecules with polar bonds. So it's got to be a polar compound to have dipole-dipole. The positive end of one molecule is attracted to the negative end of another molecule. Remember, it has to be between two molecules. Because dipole-dipole forces have to attract each other, they have to get close together. So that means the smaller the molecule, the greater the dipole attraction. If they're equal in size and mass, or pretty close to size and mass, then the stronger the polar bond is, or the more electronegativity difference you have, the stronger the intermolecular attraction is. Notice that it's going to be the negative end and positive end. The positive end's attracted to the negative. In a cluster of them, the negatives are going to slightly repel each other, while the positive and negative attract each other. So because there is some repulsion, it's keeping them a little bit apart. Hydrogen bond occurs when hydrogen is bonded to either nitrogen, oxygen, or fluorine in one molecule, and it's attracted to a nitrogen, oxygen, or fluorine in a surrounding molecule. So just like before, it's got to be between two molecules. Here we have water, and you can see the hydrogen bond between oxygen and a neighboring hydrogen atom. The hydrogen-oxygen is a covalent bond. Hydrogen bonds are so strong compared to a dipole-dipole because the polarity of the bond, nitrogen, oxygen, and fluorine are very electronegative, and because hydrogen is so small, the molecules are able to get close together. London dispersion forces are the instantaneous dipole that occur accidentally in a given atom that can then induce a similar dipole in a neighboring atom. London dispersion forces exist in all molecules, but is the only force in noble gas atoms and in nonpolar molecules. Polarizability is the ability to exhibit one of these momentary dipole interactions. For nonpolar molecules, this is very important because otherwise they wouldn't be able to attract each other to freeze. So here we have atom 1 and atom A and atom B. And so no polarization. We can say that we just have two electrons, and so they're equal distance from each other. All of a sudden we get an instantaneous dipole on atom A. Maybe both electrons wind up on the left side, leaving us with no electrons on the right, making it slightly positive. Well, that's going to cause this electron to come over to the slightly positive and make this side slightly positive or slightly negative and this one slightly positive. In which case then it would then affect the one over here and so on. The more electrons you have, the greater the chance that you're going to undergo one of these instantaneous dipoles. When you just have two electrons, the chances that they're going to be on the same side isn't as great as if you have, let's say, 5 and 3 are on the left and only 2 are on the right. They're not necessarily going to be as evenly distributed. So the strength of London forces is due to two things. The larger the atom or molecule, the stronger the London dispersion forces. And when we say larger, we are talking number of electrons. So the more electrons it has, the stronger the London dispersion force, because there's a greater chance that it's going to undergo one of these momentary dipoles. In other words, the more electrons, the greater the polarizability. An ion-induced dipole is the force of attraction between an ion and a nonpolar molecule. This ion is going to perturb the electron cloud of the nonpolar molecule. In other words, it's going to polarize it, transforming it into a temporary dipole, which then would be attracted to the ion. So we have a nonpolar molecule, hexane, and whenever chlorine comes near it, this side of hexane is going to become slightly positive, this side would become slightly negative, which then could attract the hexane molecule to the right of it, and so on and so on. A dipole-induced dipole is very similar, except the force of attraction between a polar molecule and a nonpolar molecule. So the polar molecule, just like the ion, would induce a temporary dipole in the nonpolar molecule. Larger molecules, or molecules with more electrons, are going to be more polarizable than smaller molecules since they contain more electrons, just as before. So here we have a dipole-induced dipole. We have oxygen, which is a nonpolar molecule. When water or any other permanent dipole molecule comes close to oxygen, the slightly negative oxygen is going to repel the electrons in oxygen, making that side slightly positive, and the other side slightly negative, which then in turn would affect the next neighboring one, making this side slightly positive, slightly negative, and so on. To help you determine which type of intermolecular force is occurring, you can use this flowchart for your practice problems to begin with. But realize you will not have this flowchart for any test or quiz. So the first thing you ask yourself, well, are there ions involved? If so, well, do you have polar molecules and ions? If not, it's just ionic bonding. Ionic bonding is an intramolecular force, but it can also be classified as intermolecular force because ionic bonds would be within and between them, which we'll see later. If you did have polar molecules and ions, then that's an ion dipole force. So when KBr and H2O are combining. If you don't have ions present, then are polar molecules involved? If not, the only force involved would be a London force. That would be, again, my noble gases are nonpolar molecules. If polar molecules are involved, is hydrogen atoms bonded to nitrogen, oxygen, or fluorine? If so, we have hydrogen bonding. If not, then it's just dipole-dipole. I'm going to pause the video and restart when you have the answer to these. So neon is a nonpolar molecule, so that would be London dispersion. In H3, if you draw that out, you have a lone pair of electrons on nitrogen, which makes it polar, and you have hydrogen attached to nitrogen, which is hydrogen bonding. KCl is an ionic compound, so that would have ionic intra- and intermolecular forces. pH3 is drawn just as in H3, except hydrogen is not attached to nitrogen, oxygen, or fluorine, so it's just polar or dipole-dipole. BCl3 has no lone pairs. It's a nonpolar molecule. Nonpolar making it London dispersion. Here we have two things. We have ionic and a dipole. So that would be ion dipole force. And C2H6 is a hydrocarbon, which is nonpolar, or London dispersion. Go ahead and pause the video and try this one on your own. So we're looking for the molecule that's involved in hydrogen bonding. We have COOH, which, remember, is our organic acid. And so drawing that out, organic acids have O and H, so hydrogen attached to oxygen. Water's hydrogen bonded, as is hydrogen attached to nitrogen. Here's our organic acid, and alcohols are also hydrogen bonded. Here we have hydrogen attached to itself, so that's definitely not hydrogen bonded, and iodine doesn't even have hydrogen in it. Go ahead and pause the video and try this one on your own. Restart when you have your answer. So if we're looking for the one that interacts primarily through London dispersion forces, we're looking for the nonpolar molecule. B is the only nonpolar molecule. A, C, and D are all polar. Go ahead and pause the video and draw your 3 molecules of carbon monoxide in a liquid and then as a gas. Make sure that you're indicating where your inter and intramolecular forces are. Restart when you have your answer. So first, my liquid should be near the bottom. And then we would have some attraction between the carbons and oxygen. And then our intermolecular forces. And the dashed lines are my intermolecular forces. My intramolecular forces are covalent bonds. My intermolecular forces, this is a polar molecule, so those dashed lines should be representing dipole-dipole forces. Carbon being slightly positive, oxygen being slightly negative. So gases, if you recall, the kinetic theory says that gases should be far enough away from each other that there should be no attraction. So my gases are filling my container, so they're spread out. They do have intramolecular forces. So I have some there. I have some over here. And let's put that one there. So I still have my covalent bonds because when it goes from a liquid to a gas, I do not break covalent bonds. I do, however, break my intermolecular forces, or the dipole-dipole. So you should see no dashed lines in a gas because all intermolecular forces should have been broken. So we're looking for the hydrogen bonding in methanol. Hydrogen bonding is when hydrogen is attached to nitrogen, oxygen, or fluorine. And it's attracted to a nitrogen, oxygen, or fluorine in another molecule. So in one, hydrogen is attracted to hydrogen. That's not hydrogen bonding. In two, oxygen is attracted to hydrogen, but the hydrogen that's attached or attracted to oxygen is attached to a carbon. In which case, these hydrogens are not slightly positive because this is a nonpolar bond. So 2 is incorrect. In 3, we have an oxygen attached to a hydrogen, and it's attracted to a hydrogen that's attached to an oxygen. So 3 looks good. And finally, 4, we have hydrogens attracted to hydrogens, which is not correct. So our answer was 3. Go ahead and pause the video and draw your water molecule in the correct orientation to illustrate a hydrogen bond between a molecule of water and the molecule of methanol. So first, your water molecule should be attracted to oxygen. So the hydrogen is attracted to the oxygen. We can't have oxygen attracted to the hydrogen over here because, again, just as we saw before, it has to be a hydrogen that's attached to an oxygen, nitrogen, or fluorine. And then we would have a dashed line representing our hydrogen bond, because that's what it said to use. So the dashed line is our hydrogen bond. We also could have had our hydrogen bond up here. Those would be the only 2 places that you could have your hydrogen bonds. Again, the hydrogens on the left would not be participating.